Hello everyone, my name is Soheil Yousefi from RSSL Polymer Company. Today, I will walk you through the outcomes of a 4-year reliability improvement program focused on our high temperature polymer shrink packaging systems. This study integrated RAMS engineering, reliability, availability, maintainability, and safety with OEE performance analysis, forming a unified data-driven framework for reliability growth in one of the harshest operating environments in polymer packaging. The shrink wrapping system is the critical bottleneck in our packaging line, directly affecting product flow and shipment stability. The equipment works demanding operating conditions, continuous heat cycles, polymer dust, and mechanical wear, which naturally accelerated degradation of heaters, the main switch, and sensing component. The original design capacity of the line was 300,000 tons per year, but in practice it processes over 400,000 tons, operating more than 33% above its design limit. This sustained overload increases wear-out failure mechanisms and creates ongoing reliability challenges. These conditions showed the routine maintenance alone could not address the recurring failures. A structure-based engineering approach was needed to identify root causes and improve long-term system stability. An insight supported later by pattern observed across nearly a decade of operational data. Over 10 years of operation, the shrink packaging system showed clear and repeatable failure patterns. The main switch failed about every 14 months, and the daisy chain heater diode caused cascade burnouts involving several heaters at once. The trip logic was also non-selective, so even minor events triggered full shutdowns. Weibull modeling showed beta greater than 1, confirming a time-dependent wear-out failure mode. Overall, these findings demonstrated that the system needed an engineering redesign, not just routine maintenance, to achieve a long-term stability. The original system used a daisy chain heater layout, meaning each heater depended on the previous one. A single fault could therefore spread across the entire branch. There was no electrical isolation between heaters group, which increased the chance of multi-heater failures during a single incident. The main breaker handled both normal switching and fault interruption, placing long-term mechanical and thermal stress on the device. The pressure monitoring system relied on analog pressure switches, which were sensitive to drift and environmental changes. Some things cause false trips. While this architecture worked under the initial design load, higher throughput and the equipment aging revealed the need for a more resilient and optimized control structure. In this project, we applied the structure RAMS OEE methodology to understand the real failure mechanism of the shrink machine. We analyzed 10 years of CMS data, performed RCA, FMEA, Weibull modeling, and used reliability block diagram to compare the original daisy chain design with a more resilient parallel isolated architecture. In parallel, the OE analysis helped us link technical failures to operational losses. Based on these insights, we redesigned the control and power system, upgrade sensor, and added soft tree protection. After implementation, we observed significant improvements in MTBF, OEE, and overall system stability. In this slide, you can see the main failure patterns identified from 10 years of data. Weibull analysis showed a shape factor above 1, meaning the failure rate increased over time due to wear out, not random events. The images show repeated main switch degradation and real cascade heater failures caused by the original daisy chain design, where a single fault could spread across the branch. Together, the time-based analysis and field evidence confirmed that the failures were systemic and require structural redesign rather than more corrective maintenance. In the redesign, we focus on removing single point weaknesses. We replaced daisy chain heater layout with isolated parallel control, moving switching duty from the main breaker to an AC3 contactor, upgrading analog sensors to the digital high temperature models, and added selective soft trip protection. Together, these changes significantly increase system resilience and uptime. In this slide, you can see the actual implementation in the plant. We added a dedicated C3 contactor to take over switching duty, upgrading the heater wiring into parallel isolated branches, and replace analog sensor with digital high temperature models. We also updated the PLC with selective soft trip logic to prevent unnecessary shutdown. The photo shows the final contactor installation after field testing and validation. Here you can see the performance improvements after implementation. The most important changes was the increase in MTBF. Before the design, the main switch failures occurs approximately every 14 months. After that, the MTBF increased to more than 48 months, which is a major improvement reliability. As a result of these improvements, the OE increased to roughly 90, 30, 93%, mainly because of higher availability and fewer unplanned stoppages. In this slide, you see the reliability block diagram, comparison before and after redesign. In the original series dependent design, a single heater or contactor fault could propagate through the whole branch, leading to cascade failures. In the redesigned parallel isolated model, each branch is independent. The AC3 contactor handles switching, and the main breaker acts only as an isolator. This greatly improves system resilience, and prevents multi-heater failures. From a financial perspective, the project delivered substantial saving by eliminating heater cascade failure, reducing unplanned downtime, and preventing repeated main switch replacements. The annual saving reached approximately 35,000 to $40,000. With a project cost of around $15,000, this resulted in a return of investment exceeding 200% in the first year alone. In this slide, I'll highlight the key lessons from the project. First, a structural RAMS approach using RCA variable modeling and reliability block diagram proved essential for making the right redesign decisions. Second, series-dependent architecture amplify failures, while parallel isolated designs greatly improve reliability. Third, switching duty must match component rating. Moving routing switching to an AC3 contactor reduced wear on the main breaker. Upgrading analog sensor to the digital models, and also the finally strong management of change process ensures safe and smooth implementation. These lessons can be applied to many similar industrial systems. To conclude, this project showed that a combined RAMS OE approach can reveal systematic reliability issues that routine maintenance cannot. Through data analysis, variable modeling, and reliability block diagram evaluation, we identified the real drivers of failure and redesign the control and protection logic. This resulted in higher MTBF, elimination of cascade failures, and favor noise strip and overall improvement stability and safety. The same structure approach can be extended to other critical assets supported by condition monitoring and AI-based predictive analytics. Overall, the project demonstrated how a disciplined, data-driven RAMS framework can deliver long-term reliability and strong operational. Before closing, I would like to express my sincere appreciation to Arya Polymer Company for supporting this study and enabling access to operational data and field implementation. My thanks also go to the maintenance, operations, and instrumentation teams whose collaboration and practical insights were essential to the success of this work. I appreciated the contributions of our reliability engineering colleagues who supported the RAMS analysis and verification stage. Thank you very much for your time and attention. I would be happy to answer any question.